Assalamualaikum warahmatullahi wabarakatuh and a very good morning. My name is Muhammad Shafir Abikote. Today I will present my final year project which is entitled Prediction on Combustion Pattern of CNG-DIESEL fuel engine using response surface methodology. My project was supervised by TS Dr. Abdul Hakim bin Zulkifli. This is my poster outline. In chapter 1, I will discuss about the introduction of my project, and then I proceed into the chapter 2, which is material and method that I use while carry out my experiment. In chapter 3, the analysis about the result and discussion on the experiment. Lastly, in chapter 4, which is the conclusion of my project. First and foremost, I would like to give initial description about my project. The main objective for this study is to predict the combustion pattern of CNG-DIESEL fuel engine using response surface methodology. The second objective is to graphically present the characteristic of CNG-DIESEL fuel engine in terms of ignition delay, peak pressure, combustion duration, and heat release rate compared to the diesel engine. Lastly, the objective is to validate the established predicted model using confirmation tests. Two inputs, which are CNG fraction and engine speed, were used to predict engine output characteristics based on combustion pattern. The evaluation of combustion characteristics in terms of ID, PP, HRR, and combustion durations. The numbers of runs was computed using design expert software with average error of 0.4%. The surface response analysis showed that the rate of substitution of CNG and its characteristic influenced the engine output characteristic significantly. The prediction model for ID was suggested is linear model, while PP, HRR, and CD was suggested to FI model. Using a confirmation test, the prediction models were validated and show good predictability within the 95% confidence interval. Hence, it is concluded that RSM provides prediction models with significant accuracy that predict combustion pattern, contributing to the efficiency of the conversion process for diesel CNG dual fuel engines. We proceed to my introduction of my project. CNG has a strong ability to replace conventional diesel and petrol fuels. However, application on existing diesel engine is difficult as it needs a source of ignition to be combusted. So, in addition to installing the ignition and gas fuel system, there is a need for adjustment of the compression ratio to cope with the fuel properties. Proceeding research study has reported that diesel fuel combustion has great potential to reduce more than 20% of carbon dioxide emissions. Combustion of fuels is one of the most important processes affecting performance and emission characteristics as well as engine durability. In my research, the response surface methodology is used to predict the relation between the rate of fuel substitution and the characteristic of engine output in terms of combustion patterns. The design of experiment using RSM could provide an experimental method for predicting combustion pattern responses. In addition, through its counterplot and response surface profile, these responses characteristics can be presented graphically, which are useful for established response value and operating conditions are required. The objective of the study to analyze the cylinder pressure signal of CNG-DIESEL fuel engine and investigate its combustion pattern. Then I proceed to the chapter 2, which is materials and method. In this chapter, the response surface methodology analysis, the experimental and numerical approach is combined. Numerical approach for design of experiment based on predetermined input and output variables. Experimental work is then carried out on the basis of steady-state dynamometer testing for diesel and dual fuel mode. For RSM analysis, 4 output variables are used to develop prediction models and characterization for diesel CNG dual fuel combustion pattern, which are ignition delay, instantaneous peak pressure, heat release rate, and combustion duration. This is the schematic diagram for my experiment setup. As we can see, the gases dynamometer has been used. The CNG flow rate is monitored by using the Electric Scientific Mass Flow Meter. ECU diagnostic and observe several engine conditions such as engine speed, calculate engine load, coolant temperature, manifold air pressure, and accelerator pedal position. Incidental pressure measurement is acquired by using pressure transducer. The encoder instrument was used to generate the TDC and clock signals. Both signals are conditioned by the Vitron and DV crank angle CPU. The compact DAQ and NI combustion analysis systems are used to record the data. It's connected to the crank angle encoder. It synchronizes in cylinder pressure signal in the crank angle domain. Numerical and refuel station provided fuel resources for experimentation and the fuel properties. In Chapter 3, the result and discussion based on the combustion patterns on diagnostic plot, ANOVA table, and counter response surface profile for 4 responses. This is the diagnostic plot model for peak pressure. As we can see, the normality of the residues follows a straight line, indicating that the residues are normally distributed. The data is randomly dispersed by the residuals versus predator plots, which implies that the predator models are able to navigate within the design space. The second prediction model is discussed on the ANOVA table. As we can see, the model F value of 111.46 implies the model is significant. There is only a 0.01% chance that an F value this large could occur due to noise. The predator R squared of 0.9318 is a reasonable agreement with the adjusted R squared of 0.9736. The difference is less than 0.2. Adequate precision for PP model is 23.888, which means indicates an adequate signal. This model can be used to navigate the design space. Standard deviations, mean and CV percent show as 0.1906, 9.36, and 2.04. This is the counter and response surface profile for peak pressure model. As we can see, the engine speed increases, the peak pressure has been observed to increase, but the CNG injection minimizes the pressure of the in-cylinder that shown in the counter plot and response surface profile. The maximum pressure affected by the amount of CNG injected during ignition delay and the rapid combustion period. Due to the highest self-ignition temperature of CNG, with the high CNG flow rates, diesel fuel injection decreases. The cylinder charge condition did not favor faster premix combustion. The low pressure of combustion contributes to this phenomena. This is the second response, which is ignition delay. This is the diagnostic plot for ignition delay model. As we can see, the diagnostic plot is same as the peak pressure model. The second prediction is based on the ANOVA table. From the table, we can see the model F value of 100.23 implies the model is significant. The predator R squared of 0.9225 is a reasonable agreement with the adjusted R squared of 0.9566. The difference is less than 0.2. Adequate precision for ignition delay model is 18.094, which means indicates an adequate signal. This model can be used to navigate the design space. The last prediction model is based on the counter and response surface profile. Based on the model predicted, the high rate of CNG substitution has delayed the SOC and the ignition delay duration has increased at high engine speed. The low CTN number and high auto ignition temperature of the CNG contribute to the ignition delay period and reduce the burning rate of the combustion phase. The third response is the heat release rate. This is the diagram of the diagnostic plot for HRR model. The second prediction model is based on the ANOVA table. As we can see, the model F value of 7.92 implies the model is significant. The predicted R squared of 0.4980 is a reasonable agreement with the adjusted R squared is 0.6975. Lastly is based on the counter and response surface profile. The model showed that heat release rate and engine speed as well as the RPM rise in the cylinder of engine CNG with diesel fuel for the entire range of 0% to 40%. It can be seen when the CNG energy shares increases to 40%, the highest of HRR are observed. Nevertheless, low HRR was detected at high engine speed in diesel mode. Technically, high engine speed will require high mixture of air fuel. High combustion pressure produces high air fuel mixture and leads to a high rate of heat release. The last response is combustion duration. This is a diagnostic plot for CD models. The normability of residues follow a straight line also, indicating that the residues are normally distributed. The second prediction model is based on the ANOVA table. As we can see, the model F value of 13.04 implies the model is significant. There is only a 0.46% chance that a F value dislodge could occur due to noise. The predicted R squared of 0.6469 is in a reasonable agreement with the adjusted R squared of 0.8052. The difference is less than 0.2. The last prediction model is based on the counter and response surface profile. The duration of the combustion process is the duration of the combustion process and its total duration of the flame development and the rapid combustion process. This is the burning duration behavior shows an increase in the burn time as the CNG injection flow rate increases. The highest combustion duration was predicted approximately at 1500 rpm at 40% CNG fractions. As you can see, there is my model validation for 4 responses. The developed prediction models have been validated by a confirmatory test. The confirmatory test compares the model's prediction interval with the experimental data. The first one is for confirmation test for initial delay. Based on the view of the model, overall points almost same with experimental data. The prediction model of this response is same as experimental data, where 1 point almost slip from prediction interval which at 2000 rpm and 30% CNG fraction. Generally, all the points of initial delay model's confirmation test were same enough as an experimental data. The second figure is for peak pressure model. The experimental result for peak pressure prediction model were within the prediction interval except for condition engine speed at 3000 rpm and CNG fraction at 40%, where the point observed was outside the prediction interval, and also other 1 points at 3500 rpm during same engine speed condition. Next is the model for combustion duration prediction model. For combustion duration model, 3 points are outside the prediction interval was observed for combustion duration prediction model. 2 points at 2000 rpm of engine speed during 30% and 40% CNG fraction respectively. 1 point at 1500 rpm and 4% CNG fraction show large scale of difference between prediction data and experimental data. The last one is the confirmation test for heat release rate. From the view of prediction model, a few points were recorded outside the prediction interval, especially at 30% and 40% of CNG fractions. at engine speed 2000 rpm in 30% and 40% of CNG fraction. There are 2 points outside from prediction interval due to errors detected. A large difference scale shown at 40% of CNG fraction in 1500 and 3000 rpm. Other than that, 2 points of 30% at 3000 and 3500 rpm show a minor scale difference between prediction data and experimental data. This is the diagnostics plot model for peak pressure. As we can see, the normality of the residues follows a straight line, indicating that the residues are normally distributed. The data is randomly dispersed by the residuals versus predator plots, which implies that the predator models are able to navigate within the design space. The second prediction model is discussed on the ANOVA table. As we can see, the model F value of 111.46 implies the model is significant. There is only a 0.01% chance that an F value this large could occur due to noise. The predator R squared of 0.9318 is a reasonable agreement with the adjusted R squared of 0.9736. The difference is less than 0.2. Adequate precision for PP model is 23.888, which means indicates an adequate signal. This model can be used to navigate the design space. Standard deviations, mean and CV percent show as 0.1906, 9.36 and 2.04. This is the contour and response surface profile for peak pressure model. As we can see, the engine speed increases, the peak pressure has been observed to increase, but the CNG injection minimizes the pressure of the in-cylinder that shown in the counter plot and response surface profile. The maximum pressure affected by the amount of CNG injected during ignition delay and the rapid combustion period. Due to the highest self-ignition temperature of CNG, with the high CNG flow rates, the self-fuel injection decreases. The cylinder charge condition does not favor faster premix combustion. The low pressure of combustion contributes to this phenomena. That's all from me. Thank you for watching and enjoying my final year project presentation.